lap cycles. So you can see there's really not very much motion in the top right-hand figure where we've got a large diameter to width ratio. But conversely, then if we have a very small diameter to width ratio, you can see the soil undergoes a lot more strain in this direction parallel to the wheel diameter, which is starting to confirm our hypothesis of what we've seen in the experimental data. We also have another video of this, and I hope you can see it. It can be dark, and it took us a long time to work this stuff out. But what we're looking at here is a small diameter to width ratio. And can you see these black tracer particles that are inside there? What you should note is how much more displacement goes on the front view than on the side view. So if you look on the side view, you've got some particles going down, but there's almost no dilation in the lateral direction. Here, you can see quite a lot of lateral strain going on, the particles being displaced. And that's why we figure that in this instance, if you have a small diameter to width ratio, even if you change the width very much, it doesn't register that much of an effect, because that's not the principal direction of deformation. So in a similar fashion, we updated the diameter-dependent model that we proposed earlier. But here, now we have this alpha to the QD over beta, and we needed to find a way of including the dependence of the diameter to width ratio in the pressure seepage model. So alpha and Q are just constants between 0 and 1 that describe the soil's response to a change in D over B, which is of course the exponent of that part there. And we found that using this, we were able to model, again, this comparison in the top right of theoretical and experimental data. For the quartz sand we tested, we got an R-squared of 96%, and for the Ottawa sand we got an R-squared of 95%. We also noticed for this alpha QD over B term, although it is a curved function, for relatively modest diameter to width ratios such that it might actually be used on modern UGVs, it's actually a linear function. You know, if you zoom in on that part of the graph, it's pretty linear. And so we can come up with a linearized version of the model which is simpler and knocks out one of the constants, and the slope of that is negative s. So that's what we were able to do. So in conclusion, we've seen that we've built on the previous diameter-dependent work. We've formulated two novel pressure sinkage models, one for compactive soils and one for dilated. And in future, we would like to do a lot more field test validation. And also, I would like to do tests on further, over a wider range of soils, just to confirm that these pressure sinkage models hold over a wider range. And, thanks for your attention.
Any questions for Karen? Sally?
You might not know this off the top of your head, but I was curious as you can tell me more information about the soil conditions.
Okay.
So the clay soil is what you're calling compactive.
Yeah.
So is it pretty loose?
It was pretty loose, yes. So at the moment, we're developing a fluidized test bed, the ability to control the volume fraction. But for the test that we did here, we have to prepare everything as loose as we possibly can. So it's, like I say, it was a clay silt mix, 80% clay, 20% silt.
Measure the density or
Yes, I don't remember what the numbers are.
And in the sand, is that then compacted?
Again, as loose as we can possibly get it. So the reason we're building this fluidized test bed is that we don't have any good way of ensuring that we have the same level of compaction time and time again, unless you use the same procedure to loosen up the soil and just say this is loose. You know, we can't say to any ASTM levels, this is this kind of loose sand. We prepare it in exactly the same way to a loose degree and then test it, which is why we're now building the fluidized test bed so that we can get a lot more accurate results and do tests at different levels of compaction. But then the sands have relatively little range of compaction. We're talking volume fractions probably between 55 and 63%.